Testing, testing, 1, 2, 3, testing the audio for the Cyberspectrum live stream. Okay, everyone, we're about to start.
Oh, geez. Testing, 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 testing. Okay. Testing. Is this better? Somewhere in the middle? Okay, that's good.
Okay, ladies and gentlemen, if I could have your attention and turn over here to Neil, we'll get started.
Okay, good evening, everyone. My name is Neil Pandya. Thank you all very much for coming tonight. After a brief 9-month pause, I would like to give you a very warm welcome to the 21st Cyberspectrum meetup. Tonight's event is a special edition of Cyberspectrum held during the week of Black Hat and DEF CON, located here at the SynShop Hackerspace in Henderson, Nevada. The event series serves as a forum for the exchange of knowledge and ideas, related to software-defined radio and generally aims to get people interested and excited about the applications that can be realized with SDR technology. Engineers, students, hobbyists, enthusiasts, and people of all experience levels are welcome, no matter what your hardware or software background. At each meetup, people from the community will have the opportunity to present their work, projects, and ideas to the group. The event here tonight is being sponsored by Bastille Networks and is being hosted by SynShop. Our first speaker will be Pedro Cabrera, who will give a talk titled 2G Hopping Channels Sniffing. Traffic captures in GSM networks with multiple channels and frequency hopping have been a problem that only certain high-cost devices have been able to solve. A brief review of the currently available solutions will be made, with an in-depth discussion on the Bogdan Air Probe solution in particular, polyphase filters, and the adaptations that will allow the use of low-cost devices such as Blade RF and Hack RF. Pedro Cabrera is a software-defined radio and UAV enthusiast. He has worked more than 11 years at the primary Spanish telecommunications operator, conducting security audits and pen testing in mobile and fixed networks. Beside working with the telecommunications operators, Pedro leads open source projects such as intrusion detection systems for GSM networks, which has led him to study the various fake 2G cell attacks and existing solutions. He has also collaborated in press articles on the topic, war-driven around Madrid, looking for how many and where fake stations can be found just by walking through the city. He has participated in numerous security and training events such as attacking 2G and 3G mobile networks, smartphones, and apps at Black Hat Asia, demonstrating how to remote inject commands to commercial drones at RootedCon, Information Security Conference, and showing how to spoof GPS locations using FDR, fake 2G base stations, and Wi-Fi beacon frames at the USchool Hack Security Conference. Our second speaker will be Mike Davis, who will give a talk titled Decoding and Replaying Quadcopter FPV Video. Mike will describe his attempts to track quadcopters in real time, including the HackRF SDR to process FPV, first-person view, analog video signals. He will attempt to explain how pseudo-Doppler direction finding works, as well as phase correlation. There may also be an opera cake. Mike is a software developer during the day, and in his spare time, he is the B-Sides Cape Town badge maker. After being introduced to SDRs in 2014, he quickly started breaking things, including bricking his brand new car while doing research on how car remotes work. He has given several previous talks and workshops on SDR, including hunting road Wi-Fi devices using the Hack RF and gone in 60 milliseconds from AM to open. Mike has more SDRs than sense and loves to mess with wireless microphones at conferences. I hope he's not doing that right now. He also is a part-time computer science and information graduate student at Rhodes University in Grahamstown, South Africa. Our third speaker will be Nate Temple, who will give a talk titled Better Hide Your Downlinks, Building a Budget-Friendly Azimuth Elevation Tracker. Want to get started tracking low Earth orbit satellites that require a dish? Buying an off-the-shelf tracking mount can be expensive. Nate will walk through the construction and the challenges of making a budget-friendly AS-L tracking mount from the ground up. Nate is a software engineer, SDR enthusiast, maker, and amateur radio operator. He previously presented his Etcha SDR, which is an embedded SDR device, at Cyberspectrum number 11, and he spoke at last year's Cyberspectrum meetup here at SynShop during the week of Black Hat and DEF CON. All meetup presentations will be recorded and posted online, as well as streamed live on YouTube. The videos for all the previous Cyberspectrum events have already been posted. We have a channel set up on IRC on Freenode called Cyberspectrum as a way for people remotely watching the live stream to contact the group here with any comments or questions, as well as to alert us to any audio-visual problems. The next meetup will be another special edition held in San Diego during the GNU Radio Conference, tentatively on Wednesday, September 13. We are still looking for a venue to host, so if anyone can help, please contact us. It would be very much appreciated. The GNU Radio Conference is an annual, in-depth technical SDR conference with over 300 attendees. We encourage the audience to consider attending. All the slides and presentations from last year's event are already available online, so you can decide if the event might be useful and informative to you. Further details will be posted on the meetup page about 2 weeks prior to the event, so please tune in, pun intended, for all the details, including a list of speakers and presentation topics. Future meetup locations will return to the Bay Area and will alternate every month between Noisebridge in San Francisco and the Edis Research Office in Santa Clara. We are actively looking for speakers, so if you would like to present something or if you have ideas about future topics, then please get in touch with us. We would like to thank all three of our speakers tonight for their efforts and enthusiasm, and we would also like to thank Bastille Networks for providing complimentary pizza and soda. And we would especially like to thank SynShop for providing the space here tonight and hosting the meetup. SynShop relies partially on donations for funding, so please make a donation. There's a donation bucket in the back of the room, so on your way out, anything you can give would be much appreciated. We'd also like to give a special thanks to Nate Temple, who was critical and instrumental in organizing this event tonight. So maybe we could ask for a round of applause for Nate. And so with that, we'll now get started, and I'll ask the first speaker to come forward, please.
Thank you very much, Neil. So we're just going to take a moment now as Pedro sets up, and we'll share his screen, and then we'll get underway. It's really weird hearing everything delayed by 30 seconds in here. But thank you all very much for coming out and joining us this evening after our hiatus, as Neil mentioned. Neil did put a call out for speakers in the future, especially at the Google Radio Conference, and then in the future for the Bay Area. As obvious now, we haven't done one since last October. So sorry for letting all the keen SDR enthusiasts down in that department. We've been very busy. On that note, if there actually is anyone in the Bay Area that would consider shepherding that and maybe taking over the running of that, we will be busy into the foreseeable future. So any help doing that or organizing in the future would be most welcome. So if you want to get involved, please reach out to us. And so we'll start with the next presentation in a moment.
Hi, like this?
Yeah.
Okay.
Yeah, that sounds good. I think it's too late. I think we started streaming it. You sure?
Okay.
Where do you feel comfortable standing on the stage? Because I can move the camera a little bit.
Okay.
Do you want to stand on the left or the right? Totally okay.
Right?
Okay. Take it away.
Okay.
Let's have a round of applause. Pedro.
Thank you. Thank you very much. Thank you for your introduction, and of course, thank you for the opportunity to be here today with you. This work or this time I'm showing you is I've been doing some audits into the run side or of the operators, and I have the necessity to show them the evidence of the AFF1 attack, the cryptograph attack, which leads us to intercept voice communications. Of course, the tools that we have, we need a very expensive tool, the user APN 210, using a modified version of the AirPro. Okay, so more or less my objectives here is to show you our difficulties, the frequency hopping in 2G, how channels are jumping frequency. So we need this technique from the modified version of the AirPro. But once we get into, I love the HackerF and of course the BladeRF boards. So I adapt these scripts and this AirPro because the essence of the scripts of the algorithms is the same. And of course the ability to intercept traffic. When I say intercept, please, always your own calls. I'm not pushing you or aiming you to intercept someone else's traffic. This was, as I told you, audits with the permission of the operator to record our own calls, but they wanted as evidence just our voice, our call. So we need to give them the voice. And of course, we like the HackerF. It's been ported to ARM platforms, so we can go walking with the Nexus mobile, recording the traffic, what we wanted. With the Nexus 5X, just with the OTG cable and HackerF, it's much more easier than adapting the user AP and 210 with batteries and all these things. So we fit with these solutions, and it's what we do to adapt the code. Just a little bit of context of the AirPro. AirPro, I don't know if you are used to, but it's very old. It's from the 2009, from Harald Welt, German, Hacking at Random. They show the first version, and in the same team, in the Black Hat USA 2010 with custom node, they do the full attack. AirPro was focused intercept to take traffic, and the Kraken tool from to do the cryptographic attack of the burst. But there are a lot of different modified versions that when you are a beginner, you are starting to understand. For me, at least, were a lot of confusion because some of them have limitations. The original AirPro has limitations, and there are modifications like the 2011, the AirPro GPRS that they call GPRS traffic with both downlink and uplink burst. AirPro needs the specific version of the GNU radio, but in 2014 there is a patch to be able to work with the 3.7 version. Bothgun 2014 is the first AirPro with hopping support, frequency hopping support, using the user PN 210. Then SCA playset with a bootable image, with everything together. And finally, the Piotr GSM, I think it's the most alive project doing GSM 2G interception, based, of course, on the AirPro. So the original AirPro from 2010 has all these. They are not limitations. It's what it's supposed to decode and not to decode. And of course, the big one is that the limitation in the time of the AirPro is the user P1 and the user P2. Limitations for them was of the receiver hardware, not really limitation of the AirPro, was limited to one channel. So whenever your operator is not using the hopping, it's suitable for you, but if it's hopping, you will don't see anything. There are other alternatives if you want to decode the hopping, like the Osmocom BB. They show on the CCC GSM sniffing how to do the attack, but they didn't release the code. You have the base, the Osmocom baseband has some features, but if you want to decode the traffic burst, you have to do by your own. Okay? Same year, GSM, Piotr is looking also how to overcome the problem of the hopping. And there, I think Piotr also has another solution, is to combine two RTL-SDR devices, removing the clock for one of the devices and using the same clock source. Also, both can later show a board to combine three SDR, three LTL-SDR devices. I was looking to use AirProf with a board like HackerF and BladerF, avoiding the RTL-SDR problem of the offsets and all these things. This is just a little bit of basics concepts, digital signal processing concept that I run through this adaptation process. I mix with, there are a lot of mathematical concepts, and I was always with clock rates, sample rates, too many things. And I will just to share with you my concept that I put in my mind. Bandwidth from oscillators, it's the different frequency, the range of frequencies where the amplitude falls into 3 dBs. So more or less, that was very easy to understand. Sample rate is the rhythm, how fast our analog to digital and digital to analog converter is able to transfer from the waveform, from the radio interface, into digital. Of course, it's a converter from analog to digital, I already mentioned. So how quick, how smooth it's able to do this conversion, that's sample rate. Decimation was always in the AirProf parameters. I was always dealing with decimation. What in the hell was this decimation? Decimation is the process of reducing sample rate. When we are trying to convert, when treating with discrete signals, decimation is the decreasing of our sample rate. Okay, adapting this burst, this amount of data, and the clock rate. Sample rate. Now realize, sample rate is the frequency converting analog to digital, and clock rate is the clock speed of the converter, the analog to digital converter. Okay. These four, I think, they are the most important terms that I need just to put clear when I try to get into this code. And still, time to time, the diagram of a generic SDR board. These are the antennas, the reception and the transmit antennas. With the bandpass filter, where we have the radio frequency, how they are converted into the intermediate frequency with the locus oscillator, the analog to digital, digital to analog. I want to show you this only because of the bandwidth, because I talked about bandwidth before, but there are a lot of bandwidths when we got into details, when we want to take the air. That's taken from Etu's web page. 3 general types of bandwidth: the analog bandwidth, the FPGA processing bandwidth, and our host bandwidth. Okay. Later, I will explain you why I'm so focusing or detail with the bandwidth, because when we want to receive or to intercept, to record to a file using our phone, we need to have all the components aligned, and the sample rate that we want to record must be acceptable by our memory card. That sounds stupid, but it's really a problem when you want to save to a file, that everything, the amount of data that is going through our phone gets recorded with coherent and the good speed. And just to finish with what we're going to do, to take one single file and to split into frequencies that is used in the cell, we're going to apply a polyphase channelizer filter. Okay, those filters are used to decompose our signal into number of a sub-band component, that is the frequencies that the cell is using. I recommend you further reading from Thomas Rundo, Designing, Analysis, and Synthesis Filter Banks in Junior Radio. I love this web page, I'll show you, I will share with you the link, Temrundo examples, how to play with Junior Radio, and those kind of filters, very useful when you try to decompose and play with signals. I'm finishing the theoric introductions, only to talk about the frequencies. In Europe, it's very common the extend GSM. In the United States, this is from Wikipedia, in 850 frequency band and the 1.9 gigahertz spectrum. But I was very afraid to do some real-time demo because just T-Mobile is using GSM. Okay, all of the operators or don't use these bands, or they're using CDMA. That is not is another kind of technology. So this do not apply to CDMA. So only T-Mobile is using GSM. And the time I have to play here and to take a look, they are not using frequency hopping. So I will show you data from Europe. It's more or less the same, 850, 900 in Europe. It's just a matter of frequency, okay? Frequency hopping, it's I have one broadcast cell, it's advertising. I say, hey, I'm here, I am a 2G cell, and we'll show in the system information messages the other frequencies it's using to jump, okay? In the intermediate assignment messages, when assign you another signaling channel for you, we'll say you if they are using, this is the immediate assignment, immediate. We will see if this is using the hopping and the parameters we need to hope, okay? Like the HSN, the hopping sequence number, and the mobile allocation index offset. With these two parameters, the mobile will start to jump in the same rhythm, synchronous with the baseband, with the base station. So they will jump in the same moment to the same frequency. Okay, this is the problem. The main problem is you only have one channel to sniff. We need to sniff all these channels together. It's not a real-time attack or real-time sniff. We're going to record everything in one file. That file we're going to split using the polyphase filter into several files. We will pick only the one used by our cell, by our base station, and we'll decode the GSM traffic. Okay. This is the original AirProf, the workflow, how it works from the beginning. The source is the UHD, the block, where we set the clock rate, center frequency, the gain, and the sample rate. It will do a first filter, interpolator, just as I told you at the beginning, managing with the sample rates to be aligned. Must be, of course, synchronized with the symbol rate of the GSM. The receiver is where, this is really the essence of the AirProf, where we are giving the deciphering key to decode the information. Okay. Once we have decoded the information, we are output or via string, or we can redirect to a file and record what we want, the audio, the signaling, or whatever. This is the original, limited to one channel. What does Botgun AirProf? The adaptation, what he do, he has a phase 0, where he is calculating the center frequency of the capture, okay, with some parameters like sample rate. Sample rate is how wide our capture is going to be. Once it's calculated, he will capture to a single file all the chunk of the 2G frequencies. Then we'll apply in the phase 2 the filter to split into the different channels. And only with the channels under study, under sniffing, under our work, will decode the traffic. Okay? Have you? This is how he's doing. He defined 3 different scenarios, depending on the bandwidth of our scenario, of our cell. Bandwidth, this is one channel. Okay, well, GSM channel is 200 kilohertz for one channel. Between one channel and 10 megahertz, and below 10 megahertz. Okay. He calculates here, this is the original code. He calculates the center frequency, he calculates the bandwidth. He goes to the, it's just a if case, if bandwidth is below, between, or upper, and he will use the UHD reception to C file, and will record the single file, as I told you. Then this is the polyfiles, the channelize. We'll take the file we capture to the computer. We'll apply the polyfiles filter, and the output of this filter, there are many files. Okay? Each bandwidth has a number of channels. They are fixed. We have 200 is one channel, 10 megahertz. If we divide the 10 megahertz in 200 kilohertz, we have how many channels we are capturing, 2G channels we are capturing. And below, I think it's 25 megahertz of capture, the maximum of the 210 USRP. And we'll output all these files. Next and last is to do the receiver. If you remember the last receiver, the original one, we have new values that we have new parameters to this block. In the original one, we only have the configuration. This is just when we define which channel we are working, the broadcast, the single or traffic channel, and the encryption key. Now appear 4 new parameters. These two are coming from the immediate assignment. You remember the entropy and the mobile allocation index offset, and the mobile allocation also. Okay, it's the same. How we are going to jump. With these parameters, he's able to decode our 2G traffic. Okay. That was BotGAN. A small introduction just with these two boards, HackerF and BladerF. I think most significant, UTN-210 is the capture, the density of the information recorded is 16-bit, okay? BladerF is 12-bit, and HackerF is 8-bit, okay? Clock rate, BladerF is 38.4, and HackerF 40 megahertz. And different chips, whatever. Just a small, what recall my attention, the BladerF has a flexible clocking architecture that allow us to use arbitrary sample rates. If you remember, we have 3 scenarios using different sample rates, 200 kilohertz, 10, and 25 megahertz, okay? We need to use 3 different sample rates for the 3 scenarios. If we want to maintain 3 scenarios, we could define as much scenarios as we want, but I want to keep the same. Using HackerF, this is from the GitHub from Michael Osman. Using sample rate of less than 8 megahertz is not recommended. Okay, if you take a look of the clocking of the board, preferred the max 864 clocks are 8, 10, 12.5, 16, and 20 megahertz. Okay. Why I remark that? Because if we want to start to define our similar 3 scenarios, if we want to capture just with the HackerF and the BladerF, we are going below 8 megahertz. And as it is stated in the GitHub repository, below 8 megahertz is not recommended. Okay, so we could try to use it, but we need, of course. Sorry, but I forgot to rate and sample rate. Of course, they are related with the decimation. Sample rate is my capture, my application, how much I want to capture in that moment. Clock rate is fixed value, is my board, is how my analog to digital converter is moving. So these 2 values may be synchronized, and this synchronization, let's say synchronized parameter, is the decimation. Okay? If you remember at the beginning, I was telling you that decimation is a process of downsampling, because maybe we don't want to capture at the same rhythm of the clock rate. We are using the sample rate, okay? And those are related through the decimation. So if we want to define our new 3 scenarios, we need to define sample rates we want to use when we are using a lot of channels. Sample rate when we have between 1 channel than, I don't know, this is more than 1 and less than 50, and more than 50 channels, okay? These two, I just give you those numbers, but they are absolutely not recommended. They are not out with the GSM symbol rate. So just to complete the 3 scenarios of the botgun, but not recommended at all. How to adapt the botgun airprof? It's more or less this overview. The frequency calculation, we just need to change the parameters that I saw below, the sample rate and the decimation adapted to these new boards. We will do the same. We will capture to a single file. Of course, we are not going to use the UHD. We are going to use for the HackerF, the HackerF transfer, and from the BladeRF, we are going to use the BladeRF CLI command. Of course, we need to adapt the files, the output files, 12-bit. We need to adapt them to 16-bit, okay? Not to change, of course, we will not do this step, but we will need to adapt the filter. I prefer not to touch the polyphase filter block, only to do a conversion. What we are doing is to inflate the original file, okay? We're going to create a C file, but of course, it's like padding. We are going to put zeros to the original record file from HackerF and BladeRF. But polyphase filter is not modified at all. And when we decode the channels, sure. That one? Excuse me. As the clock rate is different, in the Python airprof scripts to decode traffic, we need to tell them our clock rate when we generate those files, okay? Clock rate is not recorded in the, we are capturing file into a binary file. It's just zeros and ones. It's not information about the clock rate that we use to generate the file. So we need to give that as a parameter, okay? Again, the 3 scenarios adapted. Because of the polyphase filter, they are using internal decimations, we need to create, this is the complete map of parameters to the script. Of course, everything, there is no random value at all here, because decimations are related, and they must be related also with the clock rate of the board. Decimations could not be even, should be odd. And now that I adapt the code, I only use the extend GSM, as I told you at the beginning. Botgun use only the primary GSM, meaning that some frequencies, some ARFCNs were not calculated properly the frequency center. So I just add one line, okay, to adapt to the extended GSM. Instead of, as I told you, UHD, I'm using the HackerF transfer and the BladeRF from the capture phase. Convert the file into 16, fake 16 is not real 16-bit file, okay, we are just adding zeros. And then our polyphase channelizer is exactly the same like Botgun. And in the receiver, it's just to use 40 megahertz and 38.4 megahertz, okay? If you are using, depending on the 2 boards, the HackerF and the BladeRF. Yeah. In the introduction, I told you that I was very, one of my objectives was to use the HackerF in the Nexus. When I start to go out and use it, I made the capture. I have the single file. But when I tried to decode, I never was succeed decoding. I always have conversion error comp, I think is the law from the airprof. So I start to calculate, depending on the number of samples, the amount of samples you want to record, and how long you do the duration of the capture, you have how many, the transfer to host, how many megabytes per second you can transfer it to your computer. It's like if you see the problem end-to-end, from the radio until your, where you are storing the information, your SD card or your hard drive, whatever you are using to do the capture, to store the information, how many megabits per second you are transferring, because maybe or your hard drive is not bandwidth enough to receive all this information per second, or your USB. USB chips, they are not the same. If you're using USB 2.0, 3.0, everything changed. So you need to take a look. And of course, I realized that the SD cards, the amount of information, of course, depends of the capture you are doing. If you are going to 20 megahertz, if you are using 10 megahertz, but where it is? Yes. We can even try to record at the speed of 38 megabytes per second. That is not allowed by the SD cards, okay? If you want to ask me whatever question, if I go too fast, please raise your hand, stop me. Maybe I go too quick at the beginning, but I just want to give importance that we need to be sure that our system, that our recording system or capturing system needs to be dimensioned or seized with the sample rate we are using, because sample rate is not just a matter of how many frequencies are going to store, but we are telling our system the amount of information per second that we are going to receive in our hard drive or SD card or whatever, and should be aligned and synchronized. If not, we are going to create the file for sure, even if the bus don't allow these speeds. But when we try to decode the information, the binary file recorder is not current, is not properly recorded, and we are never being able to decode the traffic. Okay. Then this month, in the web page has some table where people upload their experience using this. Sorry, I don't know if you see something. It's very small, but they submit the model of the mobile they are using, and sometimes in the comments they told you how many megabits per second they were able to record or to transfer information. This is very useful. Okay, this some kind of information that we could use to see if we are mobile. We could record, if we are able to record, how many channels. Okay. Also, the Odroid boards, they are very suitable. They are able to use the eMMC memory. It's much more faster than the SD card. So we are able, and also has the USB 3.0. So we are able to store a lot of channels in the same time, or record captures with a lot of channels. So that was everything. I don't know if you want to do some questions. I have a file from. I am not able to do real capturing of my own traffic. I don't know if you see something here. Sorry. Do you see something there? Backward? No. Yeah. I'm trying to make it bigger, changing. Where the hell? File size. Let me do it here. I don't see anything there.
What was at the bottom of the edit menu?
Edit menu?
Edit menu at the bottom.
No. Let me open with another text editor. Okay. Now it's here. Sorry. Okay, much bigger. So the important column is this one. This is I modified the I use the Osmocom cell log binary utility to scan all the cells. This is the frequency, the ARF number, cell ID, and if they were using hopping or not, hopping frequency, just capturing the immediate assignment message, and the channels they were using. Okay, if we calculate the frequency and the bandwidth that we need, sorry, because I think they are mixing. This is the bandwidth that we need to require our SDR to capture. So some of them are 12 megahertz, 10 megahertz, 3 megahertz. Doing those kind of warp driving next to your area, or the zone you want to audit, we know where are much easier to do this, the capture with the hardware, and which were impossible. From time to time, we don't have the so fast computer of the Nexus, and we have all computers. So this is taken from the system information type 3 message, okay? And it's an automated way to just to list the cells in your zone with the parameters of the frequency hopping and the bandwidth you need for them. Sorry. Yeah. If we take a look of the output C file, when it's the original one from the user IP, if you open with the XML editor, you will realize that the 16-bit, they are complete, okay? But if the capture comes, sorry, from the HackerF, there are only 8 bits from the real and the imaginary, and same for the BladeRF, they are only using the 12, okay? So we could identify, if we have the file, the output C file, we are able to identify if we record information using the user IP, HackerF, or BladeRF.
I think Mike was going to ask that it looks like it's 16 bits of zeros and then 16 bits of data for the HackerF, right?
Sorry?
For the HackerF, it's 16 bits of zero and then 16 bits of data. What's the layout there? It's not like it's 8, 8. It's 16.
8. 4 and 4, 8. 8 for the real, and 8. I don't understand your point. 8 and 8.
It's 4 nibbles.
Yeah.
Right? So 4 times 4 is 16, which is 16 bits.
Yes, but it's the 16 in the C file. We are using, we can compare with the user IP.
Those are 32 bit flows.
It's 16 and 1632 for the whole real and imaginarium, the IQ.
Oh, okay, so it's packed.
Yeah, it's packed.
So, okay, got it. It's I and Q.
Okay. Sorry.
No, that makes perfect sense.
If you have any question, I will be more than happy.
Round of applause for us.
It's really quite a complex thing to get right.
To get?
To get right.
Yeah.
To get it right.
It's, yeah. It's, I think, took one whole month when we tried to not reverse engineer, but to get into the code of the Botgun Air probe. Of course, I am a beginner. I'm not a master of the SDR concept. There's a lot of maths behind of these terms, and to try to align all the concepts and to understand where is because our main problem is not the main, but most of the times we were able to capture, but never able to decode the information. So where to point the finger, what was That was our main problem in that whole month.
Yeah. And dealing with all this on an embedded platform and
Yeah,
it just complicates it.
it's complicated.
So there have been quite a lot of questions about the slides because I think a lot of people are interested in your calculations and numbers. So you might just want to reiterate into the microphone that the slides are going to go up on the meetup site.
Sure, no problem.
You should say it into the microphone so people, because they're asking.
Okay, the URL.
It'll go up on the meetup site.
Yeah, we'll go on the meetup side. The slides from the presentation, as you said at the beginning. Sorry.
I think some people got on late and so they were
Sure.
So it was quite dense. Okay. All right, great. Do we have any other questions from the audience here? Who has actually used AirPro before or tried to use AirPro before? A couple of you? With any luck? Or it was a bit complicated to get going? Well, hopefully they will give you some hints.
I don't go into the details of the how to do the coding, but yeah.
How, just to get some stats from the audience, who's actually looked at the GSM coverage in their local area? Who's had a look at to see how many channels there are? And has anybody seen a plethora of channels? Because usually I just see like one here in the United States. It's all 3G and LTE now. So, but you know it's still out there, and phones will still log on a 2G signal if the rest of it's being jammed. As we well know from some famous law enforcement news.
Isn't there the thing, I don't know, I think tomorrow at Black Hat there's a way where people found that you can force a downgrade from 4G to 2G. I don't know if maybe you guys know about that. I basically read the talk title and I think that's what it means.
Yeah. There are a couple of really interesting downgrade attacks.
Only fake stations are real on 2G. So from 3G and 4G, there are downgrade attacks. There are different downgrade attacks, and at the end, the fake station is waiting for you on 2G.
Right. Yeah. So it's still a deal.
Yeah. All right. One final round of applause for our speaker.
Thank you.
Thank you very much.
Thank you, Valin.
So we're just going to take a moment now to set up for our next speaker, and then we'll continue with the presentations. If you want to take this opportunity, I don't know if you want to grab another drink or another slice, or just stretch out. We'll resume in just a moment.
Okay, seems to be. Can you hear me? Okay, cool.
Give me a thumbs up. Cool. All right, so let's have a round of applause for our second speaker this evening. Take it away, Mike.
Okay, so I'm Mike, Elastic Ninja on Twitter, Dodgy Mike on GitHub. So be careful what you find there. I'm studying computer science at Rhodes University part-time, doing a master's there in information security. And in my spare time, I'm the B-Sides Cape Town badge maker. So I make hardware and other people make the software, and we do that once a year. So I'm not an electrical engineer. I'm a software developer. So all my opinions are basically things I've learned from the last 3 years or so. If I say something weird or I stick my knife into the plug or something, then you feel free to correct me. I could be easily wrong. Okay. And in fact, some of the stuff I'm doing, Balant's already done, and he's probably got a better video a better description or explanation of what I've done.
That's all. Let's hear the new version.
Okay, well.
Bring it up to date.
Okay, we'll try that. So, kind of like the reason that I'm doing this is I'm quite keen on the GSM side of things as well, but I'm trying to take things in steps. Finding FM radio stations was the first step, and this is slightly wider bandwidth. So, tracking drones is actually something slightly wider bandwidth, and it's a little baby step towards doing GSM, finding rogue GSM base stations. That's kind of what I'm trying to do. And I'm trying to do that using some form of direction finding. It's been quite a long path. I've tried all sorts of wacky things. I spent about 6 months trying to do phase correlation, and it turned out that at these frequencies, or various frequencies, you actually have to have the antennas really far apart, and that wasn't very practical. So I think during an IRC session at some stage, someone mentioned pseudo-Doppler, and I jumped straight onto that. So that's what I'm talking about today. So that's kind of why. Well, why for this particular application is quite a lot of fun. On the weekends, I go drone racing. So we go down to a field, and we put these quite fast drones. We put them through their paces, through little gates and that kind of thing. And part of the problem is lots of people in the same space with like a high bandwidth signal, and they interfere with each other, and all sorts of problems happen with that. You're busy flying 100 miles an hour, and all of a sudden you can't see anything. So that's kind of painful. So the idea was to build a system that could actually track them, and then get an antenna that actually follows the drone and gives you the best signal possible. That's the goal, and we'll see how that goes. I'm kind of doing okay. I'm about 50% of the way, I think.
Can you show the webcam a picture of your drone there?
There. So this, can you see it?
Everything's gone out of focus. Oh, there we go. Yeah. Bring it closer. You want to tell us about what kind of drone you got?
Okay, so you want to see it as well? Oh, light. So this is a Martian 2, if that means anything to people, but it's basically a racing drone. It's got some reasonable motors and that kind of thing. Goes really fast. Built it all myself, made of Chinese components that I ordered off Banggood and that kind of thing. And every single one of these is custom, so not many people that are racing like really fast builds will just buy the drones. Well, they probably buy them and then crash them into the ground, which is what I do all the time. And then they're no longer the originals because bits break off all the time. I flew this in San Francisco, and the video transmitter doesn't work anymore, so that's a lot of fun. Yeah.
What's your flight time, average flight time like that?
Depends on what I'm doing. If I'm kind of going really fast, in 1.5 minutes or so. But if I'm just taking it easy, about 3 or 4 minutes. Yeah.
Okay. And how heavy is it?
This is 480 grams, I think.
Wow.
It's pretty heavy, actually. There's better ones that chop off these parts.
Is that the weight with or without the battery pack? 480?
That is without. So that's actually a pretty heavy drone. But you can put a lot of effort into making it smaller and lighter, but then I crash all the time. So making it lighter means making it less robust, which means, I don't know. I did just a total segue. I did fly in Vegas, and I did get chased by security, so that was a lot of fun. Anyway.
So what area should we avoid?
Well, the back of the Tuscany, the parking lots at the back of Tuscany. Don't go there because they were there in 30 seconds. It was amazing. I was walking down. I sat down, started unpacking my stuff, and the guy was like, "Hey, what's up?" Okay. But anyway, yeah. So how is obviously a really good question. It's a difficult question to answer because, like I said, I've been down very many different paths. I've spent so much time on a lot of random things that were, because of some sort of small flaw in my understanding of things, I had spent 2 or 3 months on something totally random. But it's a lot of fun. I really enjoy this stuff. So obviously one of the things is to get some sort of directional antenna and point it around, and then see how strong the signal is, and you get a reasonable result with that. But I think it's not something you can automate. Like, I want an automated system that you can more or less you can have like I said, a controller that just follows the drone, and I don't want to have to kick it or point it in the right direction or do anything like that. So into pseudo Doppler. It's something that's I try to explain to people all the time, and it takes a long time. It's quite a strange thing to explain. It's a little bit of magic. I still think of it as a bit of a trick. Who knows what pseudo Doppler is? Oh, wow, okay. So maybe you guys will explain some stuff to me, but what I found is really helpful, even to people that actually know a lot about FM and about radio and that kind of thing, is actually just to start from scratch and say, what is FM demodulation? And work from there. So who knows what FM demodulation is? Same guys? No, a little bit more. Okay. So basically what you're doing here is you're taking some sort of signal in, and that's a handy sine wave. If you were to encode it as AM, you would basically take that and impose that or superimpose that on top of a carrier wave. So you can see it's very much related to that. FN's a little bit more complicated. For every change in the amplitude there, you're actually making a change in the phase of the carrier signal. So you get these little, where it's high there, you're getting them bunching together and going apart. So that phase, if you can fiddle with that phase, you actually introduce signal into the demodulated signal. And that is what you try and do. So this is my my terrible attempt at drawing my antennas and how they relate to the incoming signal. So an important thing is where you put your antennas relative to. You've got to work out the wavelength of the signal that you're trying to actually capture. So that's an important thing. And then you've got to put your antennas so that they will be a certain distance apart for that particular wavelength. And then you can see that if you do that, for this first antenna, it's going to get this particular part of the phase of the incoming signal. And if you were looking at this one instead, it's at a slightly different spot in the signal, and same there, and same there. So every antenna is at a slightly different place in the received signal. Oh, shit. So I mean, this is a really bad, sort of interpretation of it, but if you can imagine the signals actually moving and not the antennas, then you kind of start getting an idea of where, of how it's going to affect, which antennas are going to get which bit of the signal at which time. So what actually happens is if you start switching between these antennas at a certain rate, so let's say you choose, 10 kilohertz or something, you start switching between those antennas quite fast, then you're going to be adjusting the signal that you get very slightly. So it's going to be slightly move forward, move back, as you move around this particular circle here like that. And that's going to actually, when you demodulate it, you can have a little bit of extra information there. Does that make sense? Who doesn't get that? No one? Wow, okay. So
I like it. That's a great way to explain it.
is it? Okay. I've spent a lot of time with people kind of asking me questions, but So, and it kind of works. It's kind of cool. If you've seen Balant's video, he's actually driven around with that stuff on his roof. I've got it working with a little, it's for my kids, this like little FM transmitter with headphones. It's like wireless headphones. Works on 800 and something megahertz. And that was quite cool because they could wander around holding this thing, little transmitter, and I could kind of see the shift in phase as it goes back and forwards. So that was kind of cool. This is my rig. As soon as I got the, well, I'll show you the device that I've got now, but as soon as I got the device for switching the antennas, I immediately got some perspex and drilled lots of holes in it. And then I had to make my own cables. So that's, it looks pretty dodgy, and it is pretty dodgy, but it kind of works, you know. So I had to make do with what I had. So the important part of all of this is the opera cake. So it's a little plug-in to the HackerF that Michael Osman made some prototypes of, and I've got one of them. I managed to break it as well, so that wasn't very smart, but I decided part of this over here was to actually take off the antenna connectors and instead directly solder these pigtails onto it. Somewhere along there I broke it. So anyway, so I've fixed that now a little bit, and so what this does is, I don't know if you want to see it. Can I see?
Yeah, coming closer.
Okay. That's a very smart idea. Okay, so I don't know if you can really see. I can't even see that. So basically, you've got a set of connectors for different antennas. So there's an A side and a B side. You tend to basically keep these ones on that side, these ones connected on that side, and these ones connected there. So if you tell it to connect between this output port and these input ports, or the other way around, but basically you can tell it to connect between this one and any of these particular ports. And the same goes this side. So you can connect your radio to this side, and then you can basically flip up and down between these ones. So somewhere over here is a little antenna switch, and I believe there's another antenna switch over there, and one over there. So you can actually connect between there, through there, up to that side as well. So I've never done that, so I don't know if it works or not, but apparently it does. So one of the things I saw Dominic Spill doing from Grayscale Gadgets was his HackerF sweep. And then basically, so okay, sorry, I'm moving a little bit ahead of myself, but you can get the HackerF to actually tell the board to switch the different antennas if you've got the firmware. So I spent quite a bit of time fiddling with the firmware, and I haven't really got it right properly yet, but I've got something that kind of works. So Dominic's got some different firmware that's actually in the repo, I believe. And if you use HackerF sweep with this, you can get a spectrum analysis of the whole 6 gigahertz spectrum of this device. And you can switch between different antennas depending on which range you're in. So if you're in 6 gigahertz, you can be using this antenna. If you're in, you want 2.4, you can be using that antenna and that kind of thing. So that's not what I use it for, though. I've basically got it so that it's got some custom firmware on this particular HackerF. It's not actually a HackerF anymore. It's a little processor that tells this thing to what it's going to do. And this is my actual radio. So it's pretty hacky, and it's kind of a waste of a HackerF, I think. But I'm working towards getting it so that the firmware that's running in the HackerF is actually the normal firmware plus a little bit extra to get the switching going. So one of the problems I have is that in order to get this right, you need to actually know what, you need to compare that signal that's generated when you do the rotation against the actual rotation frequency and phase. And unfortunately, you don't really have that information when you do it this way. So some of the work I've been trying to do is to try and get the actual clock into the received signal, if that makes sense. So I can actually use that as my reference signal. But I'm not there yet. So anyway. That's my quadcopter of doom. I go through antennas like potato chips because the antenna is actually the thing that hits the ground most often. Right now, that's actually what went wrong with my FPV. It's sorry, FPV being first-person view. So you're actually looking outside the camera that's in front of the. Sorry. There's a nice camera in the front of the quadcopter, and when you're flying, you're actually looking. You get that view. You get the view of the camera in the quadcopter. So that's how you fly. So the next step I was trying to do.
I was going to ask on the video point, is it still the case that analog gives you the lowest latency, or is digital getting close or equal? Yeah.
The digital stuff that's out there is really, really expensive. So like nobody that I know has it. I mean, the analog's pretty good right now, yeah. And I've heard good things. We're probably getting one in like the next couple of months, so I can tell you then. But up until then, what did you find? Was it?
Oh, I mean, I haven't really played around with either. I've just heard.
Okay. Yeah, my understanding of it is there's a lot of problems with it, like reflections and that kind of thing. I don't know. We'll see. It's really expensive. It's like $2,000 or something for a kit, and the transmitter is 200 grams by itself, like in that range. So most of the guys are not keen to go for it yet. We'll see. I spend a lot of time recording and replaying FPV video. It's quite fun to watch your friends when they're busy flying and suddenly they see something, a rickroll or whatever. But it's not fun for them, but it's fun for me. So this is kind of like this is a view of the standard waterfall view of the thing. Damn it. It's actually pretty easy to start digging into NTC video. It's a nice analog, sort of 6.8 megahertz signal. And when you decode it, when you go through FM demodulation, and then you start looking at it, you can see that lovely 29.998, I think, frames per second coming through. So this is a single frame of video interlaced. So this is half of a frame really. So it's like 600 lines of frame of video. And I believe Balance is going to have some nice radio flow graphs for that in a month or so to actually decode it properly. But the work that I've done, I've got down to the, I've written a bunch of Python that can decode it, but at the moment it produces mostly noise. So it's not a very useful tool, but the idea is that I can actually decode this in real time. And it takes a lot of processing, so I'm struggling with it a bit. And it's pretty high bandwidth, so it's hard to deal with. All the problems that Pedro mentioned apply here as well, because you're pulling in 20 megasamples a second, and if you try and store it on disk or something, I actually mount RAM disks and get it to write to RAM, and then just for like, I think about 15 seconds, I can grab that in RAM, and then I stop the thing, and then I copy it to disk, and then I fiddle with it there. It's much easier. And that's it. That's what I've got to say.
Thank you, Mike.
There's a few questions behind.
So if this is for a very specific purpose, you're saying for tracking the drone to have an antenna lock onto it, have you considered adding a beacon to the craft, like a very narrowband, strong beacon? Because I think narrowband transmitters are very, very lightweight, and you just get power and put out like a 900 megahertz beacon. You just track that one signal instead of that high bandwidth signal.
That's a very smart idea. I think the actual end goal is to track other things like GSM towers or like a Stingray or whatever. But so I'm trying to learn to get to that point so I can actually do it. So I mean that is a good idea for if I just want to do FPV. So and there are actually people that have done that with they kind of, well, sorry, they use the same principles that I'm using, but they've done it in a much simpler way with directional antennas. They've actually got it right already. But this is a learning process for me. So, but I do like your idea. I think that's pretty smart.
Can you talk about the physical dimensions of your antenna array, so the relationship between the wavelength and the size and place of the antennas?
Sure. Let me see if I can find.
I'm guessing you're using 5.8 gig for your FPV video, something like that?
Yeah, it's 5.8. You know, between 5.6 something and 5.8. Yeah. Let me see if I can get. So I'm pretty simple with this stuff. I just you can ignore some of those things there. I basically have something like that. I can barely read that, but basically that's kind of the frequency that my drone's on right now. You know, the standard stuff. And so you land up with something like that. It should be 17 centimeters. Can that be right?
1.7 centimeters?
Yeah, 1.7 makes more sense. So it's hard to actually read from this angle. Yeah, sorry, 1.7 centimeters apart. That's a third of the wavelength. And then you, like, from my understanding, as long as you're within a third of the wavelength, then you don't get any extra artifacts and weird things that go on. So, so that's it, really. That's all I do.
So you're using a third of the wavelength as the separation distance of your array.
Yeah. It's kind of difficult with 5.8 because they have to actually be very close. And this is my 5.8 hat. I kind of made it in the hotel. This is all I had around, you know. But it doesn't really work. But the idea for DEF CON this year was actually to make a hat, a direction-finding hat. But I ran out of time. So, yeah.
You need to go back to 3.4 with a bit more space.
Yeah. Well, I'm actually not. I think I understand something about antennas, but I know there's a near field and a far field, and if you get them too close together, then I don't know if that affects it.
It's more on the transmit.
Is it more on the transmit? Okay. Well, I mean, they're basically sitting right on top of each other, so it's kind of even hard keeping them from just bashing each other. Anyway.
You also have to make sure your E-lines are all identical, like otherwise you get weird phase difference.
I did try that. I don't know if I got it down to the millimeter or whatever, but I got it down to, like, I was quite strict with soldering and that kind of thing. Is that what you mean, like the distance? Yeah. Sorry.
So on the opera cake,
Mm.
do you know if the switching in there is reflective or non-reflective?
I know it's one or the other. I looked it up. It's reflective, I think.
Oh, it's reflective, I think.
For this
Yeah.
case, ideally you want non-reflective for this perfect suited up.
Yeah, I think I remember looking at, I think what Ballant even did, or someone else has done it with. Anyway, I've looked at some other stuff that some people have done. And they say that you should have the one, but the other one will do. So.
It's reflective, but you can, in many configurations, use dummy loads on unused ports so that you can switch a path over to a dummy load that is absorbed.
And is it specific to the HackRF, or can it be, are they just like GPIO heads?
Well, I'll take it apart if you want to look at it. But I mean, the layout of the PCB is pretty. Oh, sorry. It fits into the HackRF, but if you had to make an adapter, but you'll make Michael sad. No, so I mean. Sorry.
We did put a header, a secondary header on it to plug into a Great Bet, which is a more general purpose microcontroller platform. And also, if you want to wire it up to your own thing, it's not very many pins that you need. Cool.
I think it's actually just using 2 pins to do the switching. It's like 4, 2 binary bits. That's pretty much it. Yeah, but one thing you should not do is remove the ports. If you ever got one, okay, because it breaks. Well, I broke it, anyway. Sorry. Okay. Any other questions? Nope? Okay.
All right, one more round of applause. Thank you very much, Mike. All right. So we've heading into our third presentation then. Nick, you wanna do it? So can we get a hint as to where you'll try racing next while you're in Vegas, so we can come and watch?
I'll probably go down to that abandoned lot again.
Yeah.
But I don't want to get arrested or anything. So.
By the way, I think your mic is still hot.
Oh, one sec.
The Tuscany, looking at the Tuscany, it's within the restricted flight zone of the airport. So that's probably why they reacted
Oh.
really quickly.
Get on the mic. 1, 2, 3. Good to go? Cool.
Round of applause to Nate. That's big.
So my talk's called Better Hide Your Downlinks. It's about building a satellite tracker. It's my Twitter and GitHub. I'll have the code posted. I got a link to it. It's just a blank repo right now, but it'll get up there after DEF CON. So why would you want to build something like that? A lot of off-the-shelf azimuth elevation controllers are pretty expensive, several $1,000s. If you're into the weather satellites or any other kind of satellites, they're all moving to higher gigahertz where you require the forward gain of a dish in order to get a good signal. And APT, which is extremely popular, runs at 137 megahertz, is going to be done after NOAA 19, which will probably be in a few years. Everything's moving to HRPT, which is a high rate picture transmission, low rate data and high rate data. There's a lot of other interesting, L-band, S-band, X-band satellites that have interesting signals on them that are worth looking at. If you do any sort of amateur deep space network tracking or radio astronomy or Earth, Moon, Earth, might be a cheap option. And of course, moving a dish, that is not fun, going out there anytime you want to change a point at a different satellite. So like a lot of my little personal projects, it starts out with a really bad picture, but it's an idea. The main idea on the whole thing was using a wheel bearing for the azimuth bearing instead of a thrust bearing. They're cheap. They're about 25 bucks on eBay, and a lot of it just bolts together. It's not really a truly SDR talk with a lot of DSP, but more of a fabrication. Some miscellaneous metalworking tools that you need. Harbor Freight doesn't have really great tools, but they're really cheap, and they do the job if you don't have to do like structural stuff and stuff like this. Or you can join, check out your local hackerspace or makerspace. Like for instance, SynShop has a full hot work station where you can weld and grind, cut metal, whatever you want to do. Might be an option. So where do you get a dish? Where can you get a dish for really cheap? A lot of times, check out Craigslist. I have a pair of 4-foot dishes. I just put an ad on Craigslist, I want big dishes. Some guy called me, said, I got 2 4-foots, bring them by for 75 bucks. Dropped them off in my driveway. And then another one, I got a pair of 10-foot C-band dishes for 100 bucks delivered. So the guy was really happy to get them out of his yard because he was going to be painting his house. Or you can look at eBay. Sometimes people will post them on eBay. If you want to buy a new one, they can kind of get expensive. But they're out there. So where do you get material for stuff like this? This is how the dish started. It was just a big old pile of metal. There's usually metal shops or whatever around the area. They'll usually have scrap bins, and you can buy the metal by the pound, which is really cheap. Or if you need special stuff like a round bar, they call it TGP, which I'll kind of go into that in a second. eBay is a pretty good option. You can buy a 2-foot piece if that's all you need, or a 1-foot piece. Other parts, nuts and bolts, eBay or your local hardware store. So to start with, one thing I didn't have was a torch. So I didn't have a good way to cut out the big 3-inch hole. So I took it to a little fab shop that was here in town. They cut that out for like 25 bucks. This is fitting up the wheel bearing. And some air tools are nice to have. And these are like carbides. Make it easy work out of that type of stuff. This was the original mount that came with it. And the idea was to flip the dish upside down because it has a 24-degree offset in it. So looking at the mount, it was square on the bottom and had an offset angle on it, so cut it apart and welded it back together. This is the first try at making the bottom, which if you're doing any sort of stuff like this, you just tack it. You don't do full welds in case you want to change it. Because I had to cut it apart. If you spun it around the corners, the edges would hit. So this was the second version. come together. I started trying with a planetary gear stepper motor, and you can find those on eBay. They're about 65 bucks, and they have quite a bit of holding torque. But I'll go into that in just a second. And you can see the how the wheel bearing kind of comes into play, holding everything together. This is the start of the top plate, and so these are called pillow block bearings. They're like a Lego piece. They're 15 bucks for the pair of them, but they have a very tight inside tolerance, and you need to get what's called a TGP. It's a turn ground polish round rod, which when it says it's 1 inch, it's 1.00 inches. And 5/1000ths matters when you can't fit in there. So this is more fitment, getting everything put together. This is the start of a top plate. I didn't really have a plan with this. It was just, throw it together. It didn't really measure much. Just, that's going to fit right about there and cut it apart. This is top set of pillow block bearings. This is where it started to get exciting. It started coming together, and this is going to work. So everything all together. Working on the bottom plate, pretty simple. Just made up some tabs and welded it all together. And I can't put a concrete post in the ground, so this is a idea I got from Marcus Leach to use some 2x6s and make a nice, easy platform. Some cheap perforated angle iron, which makes it easy to attach it, easy setup. Another shot of everything kind of coming together. And this is kind of a goofy one, but mounting the linear actuator. And started really getting exciting when it started to move. And yet again, don't fully weld something if you build something like this. You just tack it, because I had to cut it apart and redo it. I need to have it just slightly lower in order to get it fully back to 90 degrees. Then it was needed to cut some weight because it was pretty darn heavy. So the idea, my first initial idea when using the planetary gear was to basically have a 1-to-1 shaft and then use a potentiometer in order to know at what position the azimuth is pointing at any given time. So this is a mock-up of that. So then through the top, just made a quick plate out of some metal that I had around, and here's it coming together. So this is all 12mm shaft. You find it on eBay, super cheap. People make it like roller bearing, or like the slides that go for 3D printers are commonly made out of that type of stuff. Another shot of how it'll all fit with the potentiometer in there. Yet another shot here of the fitment and placing together, and the extra little brace that goes with it. And yet again, removing extra material. This stuff was 3/16. It's overbuilt by, an order of magnitude. So it was pretty exciting. Got a paint and prime. Can't really. Why didn't I? Getting everything painted and primed. I live in an HOA, and they have a no antennas policy, but if you camouflage it, they can't see it. So I'm bringing it back in, just doing final fitment, then started to work on the electronics next, more fitment. Pretty exciting to get the dish on there, and this is kind of where I figured out that the planetary gear was not going to work. So yet again, unless you're 100% sure, can I refit this? Don't fully weld anything up before you're confident. So this is the start of the electronics. Cheap power supply runs at 36 volts. It puts off like 10 amps or something like that. I think they're like 30 bucks on eBay. So for the linear actuator, there's not a lot of information online about driving linear actuators. It's just a DC motor. So a pretty inexpensive option is to use a PWM controller, a couple MOSFETs in there, and then chaining together a pair of single or double throw switches. You can reverse whether it's going forward or backwards. And then this is just a eBay stepper motor driver, which it's all very easy to integrate with, using Arduinos. And yet again, don't fully weld anything because I had to completely cut it apart. Because the planetary gear, when it's not locked, when the motor's not running, it has no holding torque. So I moved on and I picked up a worm gear. This is a 40 to 1 worm gear. We find them on eBay. I found this one for 15 bucks. Very heavy duty. Yet again, it's another Lego when you're building stuff like this. Had to mate it up with the, decided to reuse the stepper motor and planetary drive I already had. And I had to custom, I had to mill down this input shaft and with a lathe and a CNC. Here's more fitment. And here's how the potentiometer will come off the worm gear. Here is a shot of doing some work on the lathe with the output shaft. So the output shaft, if I remember, was like 18 millimeters, and the other shaft that I had was 12, and you can't really find a coupler, so it's pretty easy to just turn it down. And here's just drilled out the center and put a piece of 8 mil round stock into the end of it, and this is where the potentiometer attaches. Here's more fitment. Put together a plate to hold the potentiometer. So I'm putting it all into a box and stuffed it in there. I decided to just throw hardware at it, or in the sense of all this could probably run with one Arduino and one Raspberry Pi, but they're so cheap that it's just easier to throw hardware at it. One cool thing, which I go into a little bit later with, I'm able to remotely update the firmware on the Arduinos from the Raspberry Pi using makefiles. I have a link to a guy's repo who put that together. Pretty awesome feature to not have to go out there, unplug it, and to flash different firmware onto the device. Everything's connected to a network switch, and that runs into the main controlling PC. So finally getting it outside, leveled it up with some sand, getting everything put together. Side shot here of how the box and everything fits together. Pretty exciting to get the dish on there. And then here I just got some cheap aluminum flashing and bent it up to waterproof it. It doesn't rain much here in Vegas, so not too much of a worry for that. Moving on to the feet, I CNC'd out this center plate, piece of aluminum I had, and just used a piece of Delrin to mount that up. This is a feed I built. So this current feed is designed for HRPT, or L-band, which runs at 1.7 gigahertz roughly. This is a 5-turn helical, just a piece of copper plating behind it. There's an end connector that it's connected to, and used it in an old zip tie bottle to waterproof it and stabilize it, and a piece of foam there. Of course, you got to camo it up. That adds like 2 or 3 dB. If you want to make a helical, UHF Satcom has a pretty good write-up on it for S-band helicals. They're really wideband. I swept this on my SNA, my scalar analyzer, and it has below a 1.3 to 1 SWR from 1.4 gigahertz to over 2 gigahertz. And I designed it for 1.7, which is pretty good just by, wrapping around a bottle of, or a can of spray paint to create a coil. Here it is mounting up. I just used some double-sided foam tape to fit it up in there, to firmly attach it and epoxied it, and throw some extra silicone around it to waterproof it. Adding an extra little box. So the LNA is going to be directly attached, so you have the minimal loss. So this is a triquint. I have the part number coming up. It's a really great LNA. has a 0.3 dB noise figure, which is pretty nice to use. I forget the exact gain on it, but it works from 600 megahertz up to 6 gigahertz. Great little LNA to use for projects. Yeah, the TQP3M9037 is that LNA that is used. Some other options you can use there's an LNA for all. And there's also a semi-new SPF 5189. The 5189 has a 0.6 dB noise figure, and it works from 400 or 50 megahertz to 4 gigahertz. But they're super duper cheap. They're maybe $9. You can buy them on eBay. So kind of completed it, and yay! So I guess a couple notes on worm gears. These are really designed to use a DC motor, and they use them in things such as like wheelbarrow, like cement mixers and stuff like that. You can find these, and it's the part number with an additional N on it, which will have the NEMA flange on it, so it bolts right up to a stepper motor. You find them on eBay. They're relatively inexpensive. You can buy them even with a full, stepper motor and all connected as a kit. For filtering, these are some custom cavity filters that are produced by Sysmocom. You can find them at the URL. They are absolutely great. They have really great roll-off. They block GSM, Wi-Fi. Relatively inexpensive. And they cover quite a wide range, 1525 megahertz up to 1705.
It's great how you use the RTL for scale.
Yeah, you got to use an RTL for scale, right? Everybody knows how big that. So one of the problems I ran into was measuring the elevation of the dish. And with that, so I was using an MPU 6050. It's a 6 degree of freedom. It's a gyro and accelerometer in one little chip. So it runs over I²C. And typically that's, you're going to have a foot long trace. Like at the most, you'll use a foot of wire between whatever sensor. Well, I was trying to run this down into the box. So I was using about 10 feet of trying to run I²C over about 10 feet. It worked, but the stepper motor would create RFI, and that was really hard to pin down. I was out, out at the dish with my scope, probing, and it would work. You disconnect it and shut everything down, and it runs fine. It ran fine on the bench, and as soon as you start using, the motor starts moving, creates too much RFI. So I just took an Arduino Nano, put it in a little box, and then ran a USB cable down to the Pi. 10-foot cable works fine now. So this is mounted up under the dish, and will basically output whatever the elevation is. You don't need to have a really big dish. If you want to chase like HRPT, which I'll show you a picture of what they are, and there's a preview. The last Cyberspectrum USA Satcom had a really great talk. He has a great decoder that runs for it. You don't need a big 1.2 meter dish. You can use a $50 TP-Link Wi-Fi dish. The feed on it works fine. Or there's an LCOM dish, which is a little bit more. But these are pretty lightweight, so you don't have to overbuild it. My intention with the design that I did was to be able to, as a proof of concept, in order to build trackers for 10-foot dishes. But with something like this, with one of these smaller grid dishes, you could use a Pelco heavy-duty camera mount. These are for CCTVs. I think one of the very first Cyberspectrums in San Francisco, there was a talk about using these, or some discussion about it. They can be found on eBay. They're relatively cheap, but they do use AC for the motor, so a little bit trickier to work with. So just kind of recap before we go into the software. Two-line elements are, it's a data format, as it says. This is what a TLE looks like. These are produced by NORAD. They track every single object that they can basically see. So anything from a pea-sized piece of debris to, the space station has a 2-line element. They're constantly, I don't know exactly what the rate they are updated, but every day or two they're updated. And you can find current TLEs at the site, more information on the Wikipedia page. So going into the software, so how do you, I could have used gpredict or Orbitron, but they don't do exactly what I wanted. I just needed the basic information. I wanted to pick a satellite and give it a TLE and get back an azimuth and elevation position of whatever it is for this very second, or predictions. So there's PyFM and a link, and I got to give a shout out to Shared Brain from a blog post in 2011 where he mentions this.
I got it from someone else first.
Yeah, and
They named Nate Berge.
it's really great. It's I think you mentioned in your blog post too. That's exactly, like, you just want the azimuth elevation or the timing, a prediction of, say, and you can wrap it up, put it in a database, do whatever you want with it at that point. So it's pretty easy to use. A couple lines of code and you're getting azimuth elevation out of it. So this, like, for instance, this polls, or this sleeps for a second, so it's basically going to give you an update every second of whatever it is. So that's relatively good enough. Depending on your satellite and your frequency, sometimes you need a little bit faster update rate than that. But typically, with smaller dishes, such as like a 1.2 meter dish using L-band, your beam width is going to be a few degrees, so 1 per second is more than enough.
I got a question.
Yep.
From the internet. On the hardware side, do you ever detect any RFI from any other components?
Components?
You might want to repeat the question for the...
Oh, sure. The question was, on the RF side, do I ever detect any RFI from other components? The power supply, the stepper motors do produce a little bit as they're jogging. Typically, with stronger, like HRPT, it's strong enough that it overcomes it and it's not an issue. One thing, though, I plan on doing is completely running this off of solar power. The only thing that needs run at any sort of decent voltage is the stepper motor and the DC motor, and that's easy enough to bump up 12 to 36 volts or have a 24-volt system too. I expect that should reduce some of the RFI from that. Other than that, everything's pretty fine. It works all together, and it is under the dish. I mean, it would be nice. A lot of the amateur radio astronomy folks will contain everything within like a metal box and run fiber to avoid, so everything's contained and shielded, and just run fiber out. That's something I've thought of, but it works for what it is. So I have a blank repo. It'll be under my GitHub page. It's a placeholder. I'm going to clean it up a little bit, and after DEF CON, I'll push it up. This is the make file that I was referencing before. It's pretty great. When you use it paired with a Raspberry Pi, you push your new code to the Pi, and you can basically make, and it will install it, compile it, and install it. So my software, there's a few parts to it, and I use a ZMQ. Ooh, there we go. I use ZMQ sockets, like push and pull endpoints to basically move the information between each of the. I have separate processes for every part, basically. I'll soon have a web interface integrated to have either manual adjustments or a list of particular satellites that just a drop down and select it, and it'll move the dish to where that's at. Kind of an outline of some of the parts. There's the tracker Pi. Basically takes a TLE and it'll produce the azimuth elevation outputs. And it also, for the azimuth part, I convert it into steps. So the planetary gearbox is a 4.25 to 1, and then it's a 40 to 1. So I think it's something like 30,000 steps for half a rotation. So the tracker does that math and just feeds off whatever position and steps it should be at. Azimuth basically just controls the azimuth motor, and it reads. So one thing, I originally tried to use the ADC on the Arduinos, but I think it's like an 8-bit ADC or something like that. And it didn't, with the precision potentiometer, I think it would rotate 10 times. So for 1 degree of movement in the dish, it would move several degrees before it would change the ADC value. So how I got around that was they make little add-on boards. I think they use SPI or I2C, and basically you can get a 16-bit ADC. So instead of moving a few degrees and only getting 1 value change, for every degree now I get, I think it's 7 or 8 value points.
Another question for you.
Yep.
How does the size or diameter of the dish affect the reception? Would an old DirecTV dish work?
A DirecTV dish? So the question was, how does the size and diameter of the dish affect what you can receive, reception? So it depends on your frequency, really. That's the biggest thing. Like a DirecTV dish is going to operate in Ka or Ku band. So that's either 18 or, it's like 18 or 20 gigahertz. So your wavelength's going to be very short. So, a dish about less than a meter across is going to have a ton of gain. It has a ton of surface area to catch that signal. There is some interesting stuff up in those bands, but a lot of the, for instance, weather satellites are going to operate down in the 1.7 gigahertz area or S-band. And you really need more surface area. Typically around like a meter or larger dish is usually the recommendation. So it really depends on what frequency you're after. There are some uses for those dishes. They, for instance, like another ham radio, I think people will make like a 2-meter slot antenna. But for instance, like weather satellite tracking, L-band, S-band, they're not really useful. Couple other, so there's some Arduino code to control the stepper motor for the azimuth. The elevation, basically the logic to control the DC motor. And it gets feedback from the 6050 for the current angle. Couple other pieces of firmware. I have the names might change, but there will still be some script in the final repo. There's a debugging manual control setup. Then a simple downloader for, if you put in an array of, or a list of whatever satellites of URLs, it will go and download them every day from Celestial Track. I'm kind of jumping around here. With HRPT, it's pretty cool. You can use GNU Radio. There's in the main tree, there's several HRPT blocks, and I have them listed right here: a decoder, a deframer, and a phase lock loop blocks. So from this will basically demodulate it, and it'll give you an output file. From that output file, you can use a program called HRPT Reader. It's made by David Taylor. There's a freeware version, but if you use it, it's good to buy a license for it. You do need to change the file extension to be RAW16, otherwise the HRPT Reader won't recognize it and decode it correctly. So here's a picture of HRPT. If this is something that is interesting, I highly suggest, if you haven't seen it, to see USA Satcom's previous Cyberspectrum talk. He goes much more into detail into this, and if you follow him on Twitter, he has some really great captures. Every day pretty much he'll post a capture from Mexico to Canada. That's pretty much practically a live decode from when he posts it. So this was from my dish setup, an example of what you get from HRPT. And you can zoom in, and it has decent resolution. This is the Bay Area. Another cool thing, this isn't a dish that requires tracking by any means, but it's just a good eye candy. Inmarsat 98 West. This is 40 megahertz, I think, of L-band. So there's a lot of downlinks. This was using a B210 usurp. And another one, maybe this was the 41. One of these is 24, 5 or something. And I think this one's a 40 megahertz. And there's the Pacific Ocean region Inmarsat dish. This is barely above my horizon. I think it's like 7 degrees above my horizon. And but what's interesting in this is there's the arrow data. And zooming in, these are 2 little arrow channels. Another one, GOES 13. This one's blocked by some trees. I don't have a good view that way. So this is a EMWIM, and then I believe that's the LRIT, low rate infra. If you watch Joe's talk, he goes into quite a bit of this stuff. Something you don't see every day is an actual GPS signal. Usually it's pretty, quite a bit below the noise floor, and so it's pretty cool. If you look it up in a textbook or whatever, you'll see even the little side lobes. It's exactly how it looks.
It's really there.
Huh?
It's really there.
It's really there, yeah. The Earth is not flat. So another cool thing you can track are radio synodes. It's pretty interesting that they launch these twice a day, and this is a FSK modulated signal. There's a couple repos out there where you can decode this data and it'll give you the GPS location. And if the winds are right, you could go out and track it if you wanted and collect yourself some radio synode balloons. They go up, I think, about 20 or 30,000 feet and explode and fall down to the earth, and they track wind patterns and temperatures and stuff like that. Okay, so how about a live demo? I think we can make this work. So I'm going to be using a E310 usurp. So what's cool about this one is this usurp it does 2x2 MIMO. I'm not using 2x, it's only a single RX channel. But the key thing about this is that it has a Zinc 720 FPGA / dual core ARM. And it can run RF knock, and RF knock will, it offloads some of the heavy DSP into the FPGA where it can be parallelized. So just some notes about RF knock phosphor. It's created by Sylvain, aka TNT. There's some example flow graphs, and yet again, RF knock allows you to push semi-easily push your heavy lifting for DSP into the FPGA. This is a good example of an FFT waterfall. Because typically, one of the biggest bottlenecks is the transport link if you're trying to push a lot of data. And generally, like general purpose CPUs aren't good at, they're okay, but they're not good at, certain DSP tasks where FPGAs excel. So this allows you to do the heavy lifting and then get a low data rate. So, so this is what runs on the E-series on the embedded system, and it will push over ZMQ sync, basically some vectors for the FFT after it's computated. And then on the host side, just a ZMQ syncs, and it goes into a phosphor display, and it has a message output to push retune commands and stuff like that. Okay, so hopefully this works. I hope this works. We're running over the internet, of course, because I don't have my dish here with me. But so may need to kill this. No matter, this laptop's a demo laptop. It's getting nuked. Wait, I'm sorry, I had to get, yeah. All right.
It's going to be over the internet and through your VPN.
Yep, yeah, so yeah, I'm VPNing into a network.
Type of ampersand.
All right, so now we're SSH into the embedded usurp. And this right here is just setting up the environment to be able to use the RF knock version of UHD that's installed. So if we run that, and hopefully, oops, there we go. So obviously there's nothing good right there, but we can, oops.
What's the antenna?
This is the dish. This is hooked up to my dish right now in the yard, so I'll pull it up here in a second and move it. So this is Inmarsat 98 West. So we're looking at 56 megahertz worth of bandwidth in real time. I don't know what 15-second frame rate. Usually this would require, if you were hooked up via just this route, 200 plus megabytes per second to your host. This turns out to be 3.3 megs. So a considerable
3.3 megabits.
bytes. 3.5, 4 megabytes, yeah. So this is Inmarsat, a lot of data channels, all sorts of services. There's OuterNet, which operates off of the satellite. It's in here. But due to FT narrowband signal, it's kind of hard to see. I can adjust the gain or the bandwidth here in a second, and we can zoom in on some other signals. So, yep. No, VPN, and then this is processing it's doing all the DSP for the FFTs on the FPGA, and then it's just sending a vector of bins over ZMQ. So this is, anybody know what this one is? Any guesses? I heard it. Iridium, good job. Really fast, bursty signal, typically. If we'll zoom in, I'll change the sample rate, and we can check it out more. And then, not sure what the signal is. There are some. Anybody has a guess to what this is? I'd love to hear. It's a local signal. No, LT doesn't operate at this frequency. And for that strong of a signal, the cavity filter has such a roll off that this is like the true antenna, and this is a frequency it's operating at. So, yep, this is we're looking at 56 megahertz, like real time. Yep. Oh yeah. Certainly.
And is it active all the time?
Yes. Yep. I remember right. This is something within there's a like an aviation service or something that operates here. It's like 1670, pretty much. Let me just right here. We'll say 10 or 20. Like that? Is that better? Okay. So it's 1, 2, 3. It's like 6 or 7 megahertz wide. And I can turn the gain up quite a bit.
You haven't done any further analysis on it?
I haven't. And a little bit more zoomed in shot of the iridium. So iridium operates in low Earth orbit, and typically you don't need a dish by any means to capture iridium. But when a dish or when one of the iridium satellites from their constellation moves into the beam width, it will completely overload the front end of this setup. Oops, and we can go down and check out the. Okay, so again, GPS, pretty weak, but it's there. Can get more detail here of the various services of Inmarsat. I don't know. Is there? Do you know, Ballon, if there's clock? I don't think there's clock signals on Inmarsat.
Are you talking about the bursty thing? Is it like a a lot of the Inmarsat era stuff is PDMA, so they might just be regularly active, but we periodically
Oops. So one thing we can do is
You're gonna move
we're gonna move. Manual mode, the tracker script will typically all this data to proper locations, but whatever TI because you don't want to go out there and have to look at it if you move it and it does something really quick. Sorry about this screen resolution here. Can they hear? Is the sound good? Okay. So under this screen, this is the reading from the precision potentiometer, and if we can see, I'll try to make this. I can put in just a value of say, and another thing. So with the stepper motor, it ramps up. So if you only move, if you're only doing a small step, it will just slowly move it. But if it has to move, say, 90 degrees, it'll ramp up and start moving very fast. You can, all right, so as I change this, then we're going to see all these signals go away. We should at least. And if it was the, you can like put it right back to where it was at. No, yeah, I live in an HOA, but with the, sorry, yeah, I'm in an HOA, so, and they have like a no antenna. Live in an HOA and they have like a no antenna policy, but I have some trees and have it camoed and nobody said anything, so no complaints so far. The elevation or the elevation works pretty much the same. And one thing to note, it's here. I'm going to switch sample rate again. One interesting point to note is polarization. So what's actually on there is a left-hand. So all these strong signals are right-hand circular polarized signals, and the feed that's on there is actually a left-hand wrapped. If you were to just use it in open space without a dish, it's a left-hand circular polarized helical, because it's the dish, it flips. So all these large here are right polarized, which is called nexat, and because it's the opposite polarization. If you that signal will be, 30 dB out of the noise floor. So I guess that's almost it. So coming up soon, you gotta stay tuned for this one. This is a sneak peek to come. And yeah, so special thanks to all the RTL and RTL SDR IRC folks and HearSat folks, especially Patch Bottom, Ron, USA Satcom, UHF Satcom, Lucas. They've all helped me with miscellaneous things to build. Special thanks to Cyberspectrum for having the meetup, and special thanks to SynShop for hosting us for the talk. Right, is there any questions? No, I haven't. The question, if there was any from geosynchronous satellites, the Inmarsat satellites are synchronous or geo. Yep. Yep. Yeah, I actually I have another dish that's fixed because it doesn't move, and um, uh, this one will track those satellite dishes. They're like the geo satellites are 20 or 30,000 kilometers up. They don't move. Versus what this is made for are the low Earth orbits, which operate between 5 and 800 miles up. Um, depending, like recently, GOES 16, or GOES R, recently went up, and I have used it to swing around and watch that periodically. Not as much. There's been a big push since it has new data products on it, and it has higher resolution. Faster. It's a different modulation. There's been a big push for GOES R within the sat chasing community. So having a motorized dish is great for that if you want to swing over and look at whatever satellite really quick when you're not chasing the LEO birds. Sorry. Yeah. Yep. Yep. Sorry. Sorry, IRC. Any other questions at all? Quite a while. Weekends, and after I'm done with the day's work, and then too waiting for various parts like the PWM motor. The PWM motor, I ended up burning out some of those, and what I ended up that was a 10 amp box, and what I really actually need to do is put a flyback diode, they call it, so if a motor is turning and you stop it, it will actually produce a very high voltage reverse current, and it will fry your various electronics. And a flyback diode will basically recirculate that energy through the motor until it's done. So there was a lot of waiting for various parts. If you order stuff off of eBay, sometimes it can take 2-3 weeks or a month to get various parts. So it took a little while, a few months to build it and to read the different variations that I did of it. Basically identify, like for instance, with one of the main things with the planetary gear was that it would not stay fixed when there was no load. And being in Las Vegas, that box, it gets very hot with that power supply in it, and that's one of the reasons why I don't want to push towards using solar power. So I have another relay in there now where I will shut off that main power supply when everything's not in use. It'll just spin when you have a decent load on it. And also there's quite a bit of slop in it, in the planetary gear setup. So that's why you want to go with the worm gear setup if you can, for anything that has a good load on it. Any other questions?
That is truly a very impressive project, Nate. You've got the hardware part, the software part, and it's clear how much effort you put into it over such a considerable period of time. Thank you for sharing that with us. So that brings us to the end of tonight's Cyberspectrum. Thank you all very much again for coming down, and thank you to Synshop for hosting us for the second year in a row. So if I can remind you, please, if you consider donating to Synshop on your way out, the donation bucket is there. And thanks to Neil for his usual little intro as well. Hope you all had a good time. And as the saying goes, stay tuned until the next edition. Have a good night.